Hi guys. So I thought that I know that we already went through chapter 7, chapter 8, and we're getting ready for the test. And I know a lot of you guys are feeling a little bit overwhelmed with dealing with chapter 8 stuff. So I did wanted to clear some things up with you guys. I wanted to make this a little bit more easier and maybe just do like a little summary for you guys on the chapter 8 reactions and addition reactions. So I'm not gonna take a lot of your time. I'm possibly just gonna take like 10 to 20 minutes maximum, I promise. I don't know how long this is gonna be. It could be 5 minutes to 10 minutes to 20 minutes, but it's not gonna go over that. So for example, I did wanted to go over some definitions. So what is a hydrohalogenation reaction? It's the addition of a halogen, a hydrogen. What is a hydration? It's the addition of an OH and an H. What is a hydrogenation? It's the addition of a hydrogen and hydrogen, which you can infer a halogenation is the addition of a halogen on each side. A halohydrogen formation is an OH and a halogen on each side. And then at the hydroxylation, in which we have an OH on each side. And on addition reactions, we technically break in our double bond, and then we're adding two different groups, one group to one side of the double bond and another group on the other side of the double bond. Knowing that, that's how we get to all of the reactions that we learned for chapter 8. So for example, for dihydrohalogenation, we're adding a hydrogen and an X. An X, it's kind of like saying a halogen, which is a chlorine or bromine or iodine. So on one side we're gonna add a hydrogen, and another side we're gonna add a chlorine, bromine, or iodine. So our halogen is gonna go on the more substituted side. More substituted meaning on the side that has more carbon-carbon bonds, while our hydrogen is gonna go on the least substituted side of that double bond, which is gonna be the one with less carbon-carbons. So when we're giving on an exam, when we're giving this, like that arrow with a hydrogen and an X, it's gonna be a Markovnikov reaction. So for example, that is only when we're giving that one, but when we're giving an arrow with a hydrogen and an X but with peroxides, which is ROR, it's gonna be an anti-Markovnikov reaction, meaning that we're still adding a hydrogen and an X, but it's gonna be on the less substituted one. And so then we're gonna have our X on the least substituted and the hydrogen on the more substituted, and that's gonna be an anti-Markovnikov. So for the two of them, some things that we have to consider is that sometimes when we're adding that hydrogen and that bromine, we're gonna create a chiral center. And when we create that chiral center, most of the time we're gonna have a product, but also we're gonna have the enantiomer. So our answer is gonna be the product plus the enantiomer. And for these reactions, we have to consider something. We're able to do carbocation rearrangements. So that is something to take in mind. So for hydrohalogenation, we're able to do carbocation rearrangements. Meaning, I did put this one out as an example that, for example, we're taking this one And we know our hydrogen is gonna go on the more substituted, right? And then meaning that our positive charge is gonna go on the other way. So we have a secondary, but remember we have a secondary carbocation, but remember that we have shifts. We have hydride shifts and tertiary shifts. Oh no, we have hydride shifts and then we have metal shifts. So then we're able to, we have to look at the carbons around it. So in here we have a hydrogen, hydrogen, hydrogen. And then in here we have a hydrogen and then metal groups as well. So then if we move our positive charge to the left, technically it wouldn't be more stable because we will be making our secondary carbocation primary, but we want it to be more stable, so we need it to be either tertiary or resonance stabilized. Therefore, the only way to make it more stable, it will be if we do a carbocation rearrangement to the right, and it will be a hydride shift. So in this case, we'll get a hydride, then we'll move it in here. And then we'll have our positive charge. And then we'll have our chlorine, which is gonna be able to attack. And we'll be able to get our rearrangement product. And you can see in this case for this type of problems, our major product is mainly the rearrangement product. And I did put the mechanism just in case, so you can see we have our proton transfer, then we have our nucleophilic attack, and that's how we get our answer. Then we can go to acid catalyzed hydration. So in acid catalyzed, there's different ways that you're gonna see it. You can either see it in this form, in this other form, or in this other form. So acid catalyzed hydration is the addition of an OH and an OH and a hydrogen. Your OH will go on the more substituted and your hydrogen on the less substituted. And this is a Markovnikov addition. This one will be the mechanism for it, just in case we're doing a proton transfer, nucleophilic attack, and then a proton transfer again. So some things to consider for this reaction is that if it's chiral, we're gonna have a product plus of enantiomer. Meaning that if it's chiral, I mean like if we add our OH and we create a chiral center, then most of the time we're gonna get a product plus enantiomer. So mainly this video is mostly not really about practice problems. It's mainly just looking through all the rules for each one, because I know it is a lot and I don't want you guys to have to look through a 2-hour video for all the rules, or look through all your notes you took in class and just get overwhelmed by 70 slides. I want you to be able to use maybe screenshot this, and then just when you're solving a problem, just if you're not really sure if you got all the rules down or why you got maybe a problem incorrect, I want you to be able to see why you got it incorrect or why you got it correct, for example. So we can now go to what's the mercuration. So mercuration, you're gonna see it in this form. So meaning that in this case, our nucleophile will go on the more substituted, and our hydrogen will go on the less substituted. So for example, we have, like in here, we have our nucleophile, and then our hydrogen, the less substituted, yeah. But this is like an example, like what you will be given on a test. So for example, you see our nucleophile we're giving like, in this case, we're giving H2O, right? So another form of writing H2O is HOH. So then our nucleophile in this case will be OH, and then we have our hydrogen in there. So OH will be our nucleophile, which will go on the more substituted side of the alkene, and then hydrogen will go on the less substituted side. I just wanted to see it on a mercuration that it's not, sometimes it's not going to be H2O, it's going to be something else. So that's why I want you to be able to see it as in nucleophile and hydrogen form. So some things to consider for this reaction is that there's no carbocation rearrangement, and sometimes if a multiple choice product, it may look like this. So sometimes, like, I want you to be able to see the mechanism. Like, first of all, before your nucleophile comes in, everything's together like this. So, and then your nucleophile, when after it attacks it, it opens up. It's kind of like they're together, like in a triangle. And once your nucleophile attacks it, it kind of like opens up. But you're not really gonna see it unless the digits wouldn't really mean. But most of the time you're gonna see it like this, like which one's your nucleophile, and I think you're gonna be able to define which one's gonna be your nucleophile. So we can go to hydroboration oxidation. So when we're given this, it's mainly we're gonna do addition of hydrogen and OH. OH will go on the less substituted side, while H is gonna go on the more substituted, meaning we're gonna do an anti-Markovnikov. Some things to consider for this reaction is that if we have stereochemistry, we're gonna do syn addition, meaning that you can see here, for example, we're gonna have a hydrogen, like, we're breaking that double bond and we're adding hydrogen and OH, like we mentioned, right? So that hydrogen and OH, they're gonna be added. They both have to either be wedge or dash dash. So that means that there's no way that we're gonna add a hydrogen with a wedge and an OH with a dash. We need them to be both on wedge and dash dash. And most of the time we're gonna get a product plus enantiomer, unless of course you have to consider things like maybe you get a meso compound or you have symmetry, therefore you're just gonna get one product. But most of the time it's product plus enantiomer. So catalytic hydrogenation. So when we're given this, it's the addition of a hydrogen and hydrogen. I did circle PT because you can have a variation of a reaction. So it can be PT, but sometimes it can be PD or it can be Ni. So it can show in many different forms, as long as you have your H2. Like we mentioned, we're gonna add hydrogen on one side and a hydrogen on another side. Some things to consider for this type of reaction is that we're doing syn addition. So syn addition, again, we're gonna break that double bond and we're gonna add a hydrogen dash on one side and a hydrogen dash on the other side, or a hydrogen wedge on one side and a hydrogen wedge on one side. Just remember, we're not adding a hydrogen wedge on one side and then a hydrogen dash on the other side. They have to have a wedge or dash relationship. And again, product plus enantiomer, except if it's meso, like in this case, for example, like we end up adding our hydrogen and then our hydrogen, like on a wedge or dash dash. So after we add it, we technically have a line of symmetry, and they're pointing up on the same direction. Therefore, they're both representing the same molecule, and it will be meso. So we wouldn't get product plus enantiomer, and we will only get one product in that case. Okay, next, so then we have halogenation reaction. So that is when we add a halogen on both sides. So it's addition of X and X, like you can see here. So some things to consider: if it's chiral, it's actually gonna do an anti-addition. So in this case, for example, if we're doing Br2, like in this case, we'll break our double bond, of course, and then we'll add on one side our bromine on a wedge, and then on the other side a bromine on a dash. So therefore they need to have that wedge and dash relationship, so we can get our product plus enantiomer. And due to a mechanism on multiple choice, sometimes our answer may look like that, like what's circling here. But as long as you have the right things connected to it, I think you're able to tell. So for example, in this case, we'll get something like this, which would be kind of like a chlorine like this, and then we'll get a chlorine, then we'll have another chlorine attack it, and then this one will leave like this, which will cause it to open, and then we'll get kind of like a wedge and dash. So that's kind of like the logic behind that. Okay, so we only have 4 more. Oops. So we have halohydrin formation. So like I said, we have to remember to look at everything as a whole, because if you look at this one and then we look at this one, they can be pretty similar, right? But they don't give rise to the same product technically. So we have to be careful to remember to look at everything as a whole, because in this case, this is a halohydrin formation in which we are adding our OH and then an X or halogen. Our OH will go on the more substituted and our halogen on the less substituted. So some things to consider for this reaction is that if it's chiral, we're gonna do an anti-addition, which means that we're gonna add our OH and our X or our halogen, and they're gonna have a wedge and dash relationship. As you can see here, we add an OH and then our halogen, and they have a wedge and dash relationship. So there's no wedge or dash, it's a wedge and dash. And again, we can get product plus enantiomer. So anti-dehydroxylation, so it's the addition of an OH and an OH across an alkene. So we need to get this to be able to have an anti-addition. So we need to get that arrow, the specific arrow. So what do I mean by only? So for example, if I was in the test only given this one without, this whole thing, my answer will stop in here as an epoxide. But if I'm given everything as a whole, then I have my OH addition, which will be one in a wedge and another one in a dash. So again, some things to consider: if chiral, we have an anti-addition, we have an OH, they have wedge and dash relationship as we saw, and we're able to get our product plus an enantiomer. Well, in difference, we have acid dehydroxylation, in which, for example, we're going to be given this as our catalytic, in which instead of being, wedge and dash, they're both going to be on wedge or dash dash. And in this case, we're going to get a product plus enantiomer if it's possible. And again, this is going to be a syn addition. Like the name says, syn dihydroxylation. And then last, this one my favorite, is oxidative cleavage. And technically what we're doing is, if of course we're given this, so that's for us to be able to identify that it's an ozonolysis reaction. But now if you see it in here, we're just gonna break a double bond, and then between, like you can see, we'll break that double bond, and we're gonna create two carbonyl groups technically. So you can see it was originally like this, then we broke it, and then we added two oxygens in between, and then we created carbonyls. So the same logic goes for cyclohexanes, or like a cyclic compound. So in a cyclic compound, we do the same thing. We break that double bond, and then we put two oxygens in between. The thing is that if it's cyclic, it's gonna look a little bit more weird. So if you see, it was cyclic originally, and then it technically opened. So those ones can be tricky. So what I do is, like, you saw that I numbered everything, so I technically broke it, and then I just labeled my carbons. So let me just do this again with you guys, for example. Okay, so I have this one, and then I break my bond, and then I do my oxygen. You see that in here I don't have a hydrogen thing. I mean, I do, but it's not like, we cannot see it visually, we just know it's there. But I prefer to draw it, and here I prefer to draw it as well. So keeping that in mind, I try to make sure that I have the proper number of carbons. So for example, here I have 1, 2, 3, 4, 5, 6. So I try to count from there. So remember, in here I have my double bond oxygen. So double bond oxygen, I have 1, 2, 3, 4, 5, 6. So you see, we have the right amount of carbons. We have our two carbonyl groups. So that one will be kind of like the right answer. So you see, we just open up that cyclic compound technically. So that is mainly everything we have to know for addition reactions. So some things to keep in mind. I did get a couple of questions from like the review. So you can see sometimes we're gonna get variations of like our reactions, like D2PD. This is the same thing as if I was doing an H2PD, for example. They have the same rule, the same knowledge. It's just gonna, instead of a hydrogen, it's gonna be represented with a diorite, or like D in this case. But it's the same rules, like meaning that we're gonna get our syn addition or diorite on a dash relationship, or wedge. Let's see. Something that I did notice is that possibly the teacher that he didn't mention that if you have something like this, like 1, 2, 2A to D, 2 B, DMS, O3, CH. I'm writing it again, what I did in here. So you can see that, for example, it can look a lot just on its own, but these numbers 1, 2 is just steps. So it's technically, you don't think about everything as a whole. Like for example, you get your X, so you can get your Y, and then after you get a Y, then you can deal with this to get your C. So for example, it's a step by step. You don't do everything at once. So you do reaction 1, which will be this. to get your Y. And then after that, you can proceed to step 2 to get your product from step 2 technically. So you don't think everything as a whole. You do it step by step in those cases where you get more than one reaction. Or like you see, step 1, step 2, step 3. So I did wanted to address that because I feel like not a lot of people knew about that. And then I do want to make sure that you guys, for example, when you're doing a problem and they're asking you like, do like what used to metal painting, take the time and then just draw out your molecule. I think just drawing out your molecule, it just makes it a whole difference and it will be pretty helpful. So in case that you wanted to take like a screenshot of this, I'm just gonna take like a little second, maybe just zoom in through, like this is the whole page, and then you can zoom in through this one. You can take a screenshot of this side, then of this side, then you could take a screenshot of this side, then of this side. At last, you can take a screenshot of this, and then of this side. I really hope that you find this pretty helpful, and I know this can be a lot, and I told everyone you can practice a lot and you may feel like you haven't really, like that you don't know everything, but I think you should be fine. I was in your same position and I ended up doing better than I expected that I would have done when I got my results. And I think most of you guys, if you're putting the effort to watching the videos, doing practice problems, doing the achieves and that stuff, and even going above and beyond to going to office hours and that stuff, to be honest, I think you should be pretty good. And even not going to office hours, and if you're doing something else over that, I think you should be pretty fine. Just don't stress yourself and just do the best that you can for this exam. And look, this is one of your last exams before the final, so at least this is about to be over soon, right? Well, I really want to wish you guys good luck for Friday, and you got this.